Hi, so in the last class you saw how important is a load for a robot, where and how you can define a robot which are placed on top of the robot links, how a payload moment of inertia can be identified, how that can affect the control that we can do with the robot. Okay, so you now are very familiar with the type of loads that can be there on the robot. So today we'll do one such experiment as a case study. I am just covering that in this lecture, where I'll be explaining you how a robot actually identifies such load which are placed on top of the robot. In the last class you saw how a robot can identify that itself through some software plugins which are there in the robot controller. So today we'll just take up a small example when I'll try to determine some static loads which are placed on the robot. Not exactly the load which are placed, rather the complete load which is combined together with the added load and the link. The moment that is going to come at the joint due to that will be determined. Okay, so let us continue with today's class. Okay, so this is just an overview of today's lecture. So I'll be demonstrating the identification of a function to obtain the joint axis torque as a function of joint angle. So this is only the mechanical load that will be determined. Okay, so your electrical load will just be a function of the load, that is the mechanical load itself. Okay, so we won't talk much about the electrical load that is going to come on the actuator as of this lecture. Okay, so yes, the function may be used to estimate the mechanical load, that is the joint torque for any given supplementary load, payload, and the link system. It includes everything which are there, including the wires if it is there, or solenoid valves, or a transformer, whatever is there, corresponding to the joint angle variation. So joint torque corresponding to the joint angle variation. We'll try to figure out that. Okay, the static model is identified that can be used for performing any quasi-static task. A quasi-static tasks are the tasks which are very slow moving robot performs normally, like an assembly task. You do move your end effector with a very small motions, maybe micro motions also, but yes, robot does that task. It is as good as considering that robot to be static. Okay, so not much of dynamic torques are going to come at the joints. Okay, so assembly task, welding task, if it is welding very slow manner, then that also can be considered to be a quasi-static task. Grinding, polishing, buffing, okay, they are all quasi-static tasks in which robot constantly maintains a force normal to the surface. Okay, so it is continuously making a contact, and that motion of the robot is considered very slow. Okay, so that also is a quasi-static task. So a static model is identified that can be used for performing that quasi-static tasks. Okay, so this is today's lecture. I am going to discuss something that we have done in our lab, and how such model identification is going to help you doing load calibration thing. Okay, that we have discussed in the last class. Okay, so the identified model cannot be used for fast pick and place task such as palletizing task. Okay, that normally is performed at very high speed by any industrial robot. Okay, so this lecture will be covering only joints which are two, that is the second joint which is here, that third joint, and the fifth joint which is there. So torque, I'll be identifying the torques which are going to come on these three only. Okay, I am doing it for 6 degree of freedom KUKA KR5 arc robot, which is mounted on a flat floor. It is not mounted on the wall or on an inclined plane or on a ceiling. It is on the flat floor. That is what I am assuming. Okay, these contributes to the maximum amount of torque variation due to the influence of gravity load. So you see, at least with axis Z4 that is shown here in this figure, you see if this is rotating, okay, and you have a load which is fixed somewhere over here, because the load rotates almost along its own axis, there is hardly any torque variation which is created at any of the joints because of its motion, because of this motion. It will have some effect on axis 5 if it is rotating, okay, that torque will cyclically change in a sinusoidal manner, that is fine, but the variation that is over here and over here is almost minimal, okay. So yes, I am not considering any Z4 axis torque. Also, I am not considering the torque which is going to come over here, that is Z1, okay. You see it is parallel to G. If I move the robot anywhere in this sagittal plane is the plane which passes through all the axes together. So this is a plane like this one, okay. Whole of the robot at one instant of time can lie in that sagittal plane. It becomes a planar robot. Everything works on that plane, okay. If it is moving in this plane, okay, so there won't be any torque that is going to come because of those motions on axis 1 also, okay. So this is a sagittal plane motion. So the joints that I am considering is joint 2, joint 3 and joint 5 only of a 6 degree of freedom KUKA KR5 arc robot, okay. So let us move. So let me just recall some fundamentals here. That is the joint torque relation of a serial robot in sagittal plane. So these are the two links that I am considering. This is link I-1 and this is your link I, okay. In this figure you see torque I may be given as tau I, this is a scalar value, is mi is the mass of this link, ith link, g is acceleration due to gravity, okay. So that is the force which is acting, mig is the force acting downwards, and this is your center of gravity location here, okay. And you have a vector given by di that connects the axis of rotation to the center of gravity location, okay. This vector is in plane. So if I connect two axes OI and OI plus 1, so you see there are two angles. So psi I is the angle which is defined and that is fixed for the center of gravity location referred along OI plus 1 with reference to OI plus 1. So this psi I, that is a constant. So di has two projection, dix and diy. These two projections are not going to change because center of gravity location is not going to change if it is referred with respect to OI frame, okay, with axis xi plus 1, yi plus 1 all defined, okay. So if it is referred with this frame, so it is fixed, okay. So dix and diy is not going to change. Now there is another angle, that is xi I. So this is the effective angle with which this link is going to rotate, okay. So this is the horizontal reference frame. So this is perpendicular to the z direction, okay. So this is there. So this is angle which is measured with this horizontal reference frame, not necessarily the joint angle. Joint angle is something else. So it is, joint angle is basically angle between xi and xi plus 1 measured in this plane only, okay. So that is not I am going to consider now. So I have just taken psi I which is measured within this plane and from this horizontal axis xl, okay. So this is your angle and this is your line which is making some angle with this. This is the horizontal line. So you can now see this clearly. So this is your angle. So effectively tau I is equal to mi di g cos xi I plus phi I. Let me just clean it up once again. Okay, so now you can see this very clearly. So this is your angle this angle plus this angle, sum of that is this angle. So that is shown here. Okay, so you have two projections of di, that is along x and along y, and because of that, so di cosine, so this is your distance, so it is over here. So this is the effective arm on which MIG is acting. So di cosines xi I plus phi I into MIG. So that is the effective torque that is along this axis. So that is tau I. Okay, so this is first thing. And next one is the recursive torque relation is given as tau I minus 1. So whatever you see over here, tau I minus 1 is because of the torque which is here already. So this is your tau I, this is your tau I minus 1, sum of whatever torque that is going to come because of the center of gravity, torque which is created due to the center of gravity of this. Okay, so that is the torque, that is the additional torque. So you see, if you have a link which is here, if you have another link which comes here, if you want to calculate tau I minus 1, okay, and there is already tau I over here, so torque over here will be sum of torque which is here and torque which is caused due to the pull which is on this link itself. So torque which is here plus torque due to this is the total torque that comes over here. So that is what is stated vectorially out here. So this is already covered earlier in our robot statics also. So these are the two fundamental things that you should just recall. Okay, so now let us move how to do this identification procedure. So the variation of torques is sinusoidal in nature. You have seen just now for any single link if it is moved in a plane parallel to G. Okay, so this is what you have seen just now. Next, the Fourier approximation as given by Atkinson et al. 1985 was used to best fit the curves which are obtained by changing the angle psi I. Okay, so if you change this angle, okay, the angle which is here, you see, if you change this angle, you can only change this angle, you cannot change this is fixed. So when this link is making any motion, okay, so that is what is shown here. So if that variation is there, torque will change like this. This is a constant. Okay, so torque at ith joint is given by this. A0, An and Bn are the coefficients of the series function. This is effectively a series. Okay, normally we see only the first order, that is what is appearing in our previous equation. N is the order of this series which is an integer, and psi I is the swept angle by this link I. Okay, so this is this model we are considering will be taking n is equal to 1 as you have seen in our previous equation. So that will basically converge to the previous equation if you take n is equal to 1, and I'll obtain all the data. I'll make the robot link move and I'll obtain the torque corresponding to the joint angle, and I'll try to fit it to this. This is what is our job, and I'll try to get these constants. Okay, in order to do that, I'll capture all the data while moving the robot, and using MATLAB function fit xy and the type of fit, I can do that. So where x is an independent variable, in this case it is theta, that is the joint angle. Okay, y is the dependent variable, in over here it is tau, that is the joint torque, and fit type is the order of approximation. I told it should be 1 for our case. The function returns the value of Fourier coefficients. Those are An, Bn and A0. Okay. You saw torque is a function of sine A and cosine. This constant is appearing because of some sort of idle torque which is there, maybe because of friction. Okay. So KUKA robot sensory interface, KUKA RSI, I am going to use KUKA KR5 ARC robot as I told. So I am going to use this add-on now that allows me to obtain the joint torques and the motor currents corresponding to the joint angles. So if I move this robot, I can use this add-on to obtain all the joint torques. Mind it, this robot doesn't have any inbuilt torque sensor at its joint, so probably it has a model of its motor which can get, because you can measure the current, so using that current it effectively calculates the torque and it gives you using KUKA RSI. Okay, so I'll be obtaining that torque basically. Okay, so let me just start identification procedure now. So these are the steps. In the first case, I started with the last link first. Okay, I started moving link 5. So link 5 and link 6 will move together. As I have told, moving link 6 will not cause much of a change in the joint torque. So I am just excluding that. Anyway, I want to keep my robot in the sagittal plane only. So that is why I am moving this first, and this you already know by your existing knowledge in case of robot. So you have to come from something that is already known in hand. So you know everything about this. So torque, there is no torque which is going to come over here. That is the reason I am moving this first. If I move this, torque variation will be there, and that is only because of this link motion, and there is no torque at this end. Okay, so that is the reason I started here first, and then iteratively I'll come back. Okay, because while moving this link, I already have the torque variation at this joint. I'll obtain the model of this link first, then I'll do tau I minus 1 if this is link I. So if this is already obtained by the previous motion, this can be obtained by the motion over here and the torque which is over here, and finally this can be obtained. So this is the reason I am moving backward. Okay, torque is to be calculated in the backward manner. You have seen in the earlier examples also, earlier cases when we were doing statics also. Okay, so the torque changes by changing any of the joint angles 5, 3 or 2. Okay, hence it is expressed as tau 5. You see, torque 5 changes. Torque 5 is a function of theta 5, theta 3 and theta 2. Any of these, if they are changing, torque 5 is going to change. Is it not? You see, if you have a link which is one after the other, okay, so any of these, if it is changed, okay, if you change this, you are going to see some change over here. This is your torque 5. So even if this is moving, this is going to change. If this is moving, this is going to change. Any of the prior link also, if it is moving, this is going to change. Okay, this torque will vary because effectively whole of this link is moving with respect to the z direction. So that makes this change. So this is valid. So tau 5 is a function of theta 5, theta 3 and theta 2. Okay, so the data is obtained while link 5 is moving, and combined swept angles. So psi 5 is equal to theta 5, theta 3 and theta 3 sum together was fitted in this Fourier fit function, and coefficients were obtained. So you see, once I acquire the data of tau 5 and this angle, okay, so I have put them together and used MATLAB fit function to obtain the coefficients. What I got is something like this. So tau 5 is equal to this is A0, this and this. Okay, so these two are the coefficients I wanted to have. A0 may be attributed, that is because of friction it is going to come. Okay, and it is a very less value, so I am simply ignoring it to make it purely sinusoidal manner. So that is what is giving me to this. Okay, so this and this are the coefficients that I could get. Now theta 2 and theta 3 were kept as 90 and minus 90 respectively. The way I have shown in my first figure, okay, that is the cannon position the robot was. So in that case, these two are like this. In that case, psi 5 is equal to theta 5. This is minus 90, this is plus 90. So this becomes equal to this. Okay. Okay. Now this implies that the unknowns are this. So effectively the dx component comes here and dy component comes here. So you saw you had two projections of d, and those were causing the moment at the joint, and moment projected along the axis is exactly the same, that is the magnitude of the axis, because the robot is in sagittal plane. So you see these two should be same. So m5d 5yg is equal to 4.9 and the x component goes here. So those two are the moments that is directly appearing here. Okay. So let me just show you that figure once again. Okay, so you see you have equation which is given like this. So this basically has got two components. This torque has got two components. One is because of the component which is over here, and next one is because of the component which is here. So dx, so your force mig acts over here, and it is creating due to this distance first, that is first torque which is going to come, and that will be your cosine component, and this is also there, this y component, and you have that force that is acting due to the mass is acting downward, that also is creating a moment over here, and those two combined together is shown like that. Okay, so you have two components, that is mi dxig and mi dyig component. One will be cosine, other will be sine component. Got it? Okay, so now you see you got to this. Okay, so the first motion is done. This model is identified already, that is the top 5 model for the motion is already identified. Now going to the third link motion. Okay, joint 3 was moved and corresponding joint torque T3 was recorded, and again using Fourier fit approximation gave me this equation. This is tau 3 equation. Okay, now tau 3 was moved about its mean position, that is cannon position, if you remember. So this is your link, this is your axis, these are your axes, and this is your thing, and this is your second link, this is your third, and this is your fifth. Okay, so now I am talking about this. So it was in elbow position like that. Okay, that is the cannon position. In that case it was having minus 90 degree, theta 5 is equal to 0. Okay, and swept angle psi 5 is with respect to the horizontal line, that will be given as this. Psi 5 will be equal to theta 3 minus 19. You see, if theta 3 is equal to 0 degree, it comes totally like this. In that case it goes to minus 90 degree, is it not? So measured with respect to the ground, you see this is with respect to the ground, so it comes perfectly like this. Okay, so in that case it is minus 90 degrees. So that is what, so this is there. Okay, now using backward recursion, T3 can be written as T3 is equal to T5 and this, is it not? So if you see, this is your fifth link, this is your third link, forget about fourth because that is, we are not moving, assuming it is frozen. So fifth and third, so I am talking about this, so that comes here, T5 comes here. Okay, and this is due to the link which is here, is it not? So that is what is making this. Okay, now substituting T3 and T5 that we have obtained earlier, model was already identified. So if I substitute this and the previous T5 to these locations, so I can write this equation like this. Okay, so the same thing will come here, and this is because of sum of T3 and T5. So substituting all the joint angles, I got this. Okay. Now the unknown mass moments are, in this case I have split this once again the way we did it for fifth one. So this is 88.86 that comes here, and this one should be because of this. Okay, got it? So this is already here. Okay, so unknowns are identified once again. The torque 2, okay, is now recorded. Now I am moving joint 2, okay, and tau 2 is recorded, keeping joint angles theta 3 and theta 5 as 0. In this case, psi 2 will be equal to theta 2. The torque is expressed as this. Using Fourier fit, I could obtain this, and it didn't had any next value, any sine A value, because this link was straight now and it was symmetrical. So hopefully that CG was lying on that axis itself, and this can iteratively be written like tau 2 is equal to tau 3 plus this. Got it? Which gives unknown which is only along x as this. There is no y offset which is there. Okay, center of gravity lies in the line which connects both the joints, which are here, which are here. Okay, I'll show you in the figure also. Okay, you have these two joints are there, so you found out this, and you see it is not at an offset. Okay, it is exactly lying in the on the line that connects both the joints. So that is what I am talking about. And in this case you had some kind of shift along y-axis. When you were talking about this, the CG was not lying in the line that connects these two. Okay, now summing them all together, I have obtained mass moments for all the links, all the components I have obtained. So putting them all together, the identified mass moments are now put together in this table like this. So whatever values I have obtained were these, divided by G, which was there, it gives you these values. And that is done for all the three links that I have moved. Okay. So yes, now let me show you what actually is done. Okay. I have some videos that will demonstrate exactly what was done. So yes, so this is the experiment. This is the data you see on the right side of it. You see the robot. This is the axis 2 which is in motion now, and data is getting acquired in the right side of it. Continuously I have acquired using RSI monitor over here, KUKA RSI. Okay, this is the torque which is getting captured over here. Okay. Now axis 2 comes to rest and axis 3 starts doing that motion. Okay, and now again the data is getting captured. All the axis joint torques are getting captured. Okay, joint angle is also recorded. Now axis 5 is moving. So these are the motions that this robot has made. Got it? Okay. So this is how I made the robot move, acquired the data, did Fourier fit, and I could get the mass moments which was actually responsible to do the torque changes that you have noticed. Okay, so using this, whole of the model is now identified, and I am using those mass moments now to test whether it can give me actual torque. Okay, so this is the test trajectory, that is in sagittal plane motion only, without moving joint 4 and joint 6. I am making some straight motion like this. This also is not moving also. So only this and this is moving. So axis 2 I have made it move from minus 45 to minus 90. Joint 3 30 to 50, and joint 5 minus 90 to plus 90. So these are the variations. This is the test joint angles with time that is done. This gave me torque variation like this for all the joints. So this is for second joint, this is for third joint, and this is for the fifth joint. So as expected, dotted ones what you can see here are the predicted ones, okay, and the continuous one which are there are the actual ones. So both are exactly overlapping. You see, for this test trajectory, it closely matches, it exactly matches to this, okay. So using this you can predict the load which is going to come, and mind it, whole of this model was identified with all the supplementary loads in place. If load is there, it is already fitted. I have acquired data for that. I have identified my mass moments with that, and because it is identified with all those loads, the torque that I am going to get out of my model is exactly the torque which is going to come, not with the bare robot but with the loads which are there, okay. So this will help me to identify if there is any overload, if it is there. So this is how even robot manufacturers are able to calculate this torque, okay, and they already have the mass moment of the link itself. Those they can easily segregate this added mass from the link mass. In my case, the link mass and the added mass are considered together, and I could get the mass moments, okay. So this is a very good demonstration in which an identification procedure you have seen, which exactly can tell you if your link is going to be overloaded, your joints are going to be overloaded. But yes, it is purely mechanical. A similar procedure may be used to obtain the electrical loading also for the motor corresponding to the joint angle variation. But you see, if torque is higher, current is going to be higher. So it should follow the profile which is here for the torque also. So that is what is expected. Okay, so with that, I would end here. In the next class, we'll do repeatability test, and explicitly I'll discuss ISO 9283, that is a performance test criterion that is defined in this ISO class. So repeatability test is one of them. So we'll discuss very much in detail for that. So with that, we'll end today. That's all. Thanks a lot.